Hello, everyone. So I guess this is a timely talk for FRBs, considering the Shaw Award for Astronomy was announced yesterday, and it went to the discovery of FRBs back in 2007. And so I'll talk a bit about FRBs, but mostly the host galaxies. So FRBs are extremely energetic bursts of radio emission. They come from all parts of the universe, and they go off in about a millisecond. And they can act as excellent probes of anything with it between where the burst goes off and the observer. So you can see here, as the burst, there's a dispersion based on the frequency of the light. So the greater the dispersion, the more material that runs into, or the further away that these bursts originate. And so we have all these extremely energetic bursts, and they tell us a lot of information, such as solving or trying to solve the missing baryon problem, which was mentioned a couple of talks ago. But as useful as these bursts are, the origins and what creates these bursts is still unknown. And so one way to figure it out is to figure out where these bursts are formed, the locations of which they're formed, and what creates FRB progenitors. And so some FRBs repeat up to tens to thousands or thousands bursts, right? And so those ones are easier to locate. But then there's other ones that seem to only go off once. And so is it a mechanism that creates both of these, or are they totally separate? Ones that are repeating, they're easier to localize, but then there's the ones that don't repeat. And so the ones that don't repeat, most of them have been localized by the Kraft survey. So Kraft uses ASCAP to localize these FRBs by being able to do a data drop and data dump of the actual voltages. And with enough spectral resolution, they can figure out where these FRBs originated, up to sub-arc seconds, depending on the pipeline they're using. And so their goal is to detect as many FRBs as possible and try to localize where they are. Once they can localize the host galaxies, they can examine the environments and try to figure out what causes these FRBs. And so an early detection from Kraft is this FRB listed here. I won't run out the phone number, but you can see it there. And so it was detected with one of the lowest dispersion measures. So again, it went through minimal amounts of material. So therefore, it's probably one of the closest FRBs. And so this one was detected before the Saleh pipeline, so before that 3-second voltage drop that I mentioned. And so to figure out where it was, to localize it, they used the signal to noise between adjacent ASCAP beams. And as you saw in previous slides, ASCAP has a whole bunch of beams. And then if you do the signal to noise, you can kind of triangulate where it was the brightest, and that's kind of the location. And so that's what they did for this one. And they localized it to this region of sky. Again, because this one had the lowest dispersion measure that they had detected, they then were able to cross out which galaxies it might come from, right? And because they were able to eliminate some background galaxies, and then they found a couple that were nearby, and basically only one which was close enough to host this FRB. And so in that little GMOS cutout there in the bottom, you can see it's this one galaxy. It's kind of a disc-like structure, and it has a bit of a stellar shred to the south. At that point in time, they're like, it looks like an interacting system. And so the Kraft people contacted their friendly H1 astronomer, and they're like, do you want to do some FRB science? And so I followed up using ACA, and we were able to see a bit more about this galaxy. And we also got some deeper Gemini observations. And so you can see there's this disk-like galaxy there and this stellar shred to the south. There's also this H1 tail that extends to the west, kind of perpendicular. And so we're seeing that this is an actively interacting system. It's at least one close passage and possibly more, because it's shredding both the H1 and the stars in that bottom feature there. And so that bottom feature is around 10% the mass of the larger galaxy. So it's more of a minor merger is what we're looking at. And so now that we've detected this system, we're looking at other systems to see if those also have interacting or other turbulent type features. And so I will note that this was one of the closest FRBs. It's actually the closest non-repeater, but there's a few others that do repeat. And so follow-up observations were able to be done on those ones. And so here's an example by Kerr, where they've got some GMRT H1 maps on this repeater galaxy. And you can see that also this one looks kind of disturbed. The morphology is not very symmetrical. There's something going on. And so possibly an interaction or some other turbulent force that's happening. And we keep going with this trend. And so here's a couple of galaxies, extragalactic ones, where they're taken with green bank telescopes. So you can see that the spectra in them are totally have an asymmetry. And so that again indicates some kind of an interaction or disturbance or something that's making the gas kind of different, and possibly the thing that's causing these FRB progenitors. We also have a bonus one. And so now we're moving towards the more recently detected craft FRBs. And so this one was using that SALA-B pipeline. So they were able to localize it to subarc-second levels. And you can see it right there. So it's localized to that galaxy. They're able to get some ALMA data on that. And again, we see this asymmetry. So there's something going on. There's some kind of a turbulence in there, and that's in the CO gas. But then we go to our most recent detection with Kraft and Wallaby. So this was a commensal detection. So the C in Kraft is for commensal. And so Kraft can observe whenever any other survey is observing on ASCAP. And so it happened that Wallaby was observing in H1, and an FRB went off, got some voltage, got the voltage dump, was able to localize that FRB to that little ellipse right in that center of that image. And so it's right from that core of this very nice spiral galaxy. And so this one looks very symmetric compared to the other ones. And so now we're thinking, okay, are we shifting this trend? At first, it's like all these FRBs are coming from these interacting systems or, turbulence, something going on. But now this one looks quiet compared to all those. And so again, we're dealing with small number statistics, but this one is showing that we don't know that much, and we still need to study more of these things. And so here is the summary of those FRBs. And so we're seeing that some of them repeat, some of them don't. Again, we're not sure if it's the same mechanisms that create these FRB progenitors that then form an FRB. And so we have different results, and all these are the closest ones. And so the thing is, we can only do this type of detailed research with very close FRBs. And so we want to detect hopefully more FRBs. And as more FRBs are detected, we'll be able to have more statistics and be able to follow up on more of these host systems. And so as we're going through, we are finding more and more hosts. And so the most recent one, so that one that I mentioned, that Wallaby FRB, which I'll also mention, had a press release last week that Martin did quite well in. We have some Meerkat follow-up data on, and you can see it's extremely symmetrical, right? So I alluded that it looked kind of, undisturbed. It was a nice, pretty spiral galaxy. Well, in this image here, you can see the spectrum. There's no disturbance. It looks like a nice disky galaxy, kind of boring because I like interactions. But again, this is the science that's telling us. And then we followed up on another one using Meerkat as well. And we are starting to finding that at least all the close ones do have H1. So they have stars, they have gas, there's something going on. Is it interactions? Possibly, maybe not, but we'll see. And that's basically it. Thank you.